Good afternoon, everybody, and thank you for making it to this session on marine cloud brightening. This afternoon we have 4 presenters who will have 15 minutes each to give us a presentation on their research. And at the end of the 4th presentation, we will then have a Q&A session. So I will encourage you to write down your questions as soon as they come into your mind, so that you don't forget them at the end. So we're having some technical issues, but don't worry, nothing to worry about. So soon we will start, and hopefully in a couple of minutes. Thank you for your patience. So I can start presenting the first presenter. The first presenter is Annelot who is a researcher at the Delft University of Technology in the Netherlands. And her research is on evaluating the impact of saltwater spray strategy and evaporative cooling on marine cloud brightening effectiveness with DALES. Is that right? Cool. So who is Annelot? So Annelot is an applied physicist whose research focuses on the effect of saltwater spray strategies in the atmosphere for marine cloud brightening with large eddy simulations. And she has done a lot of work, some of which include assessing the impact of anticipated land use changes due to climate change on local water patterns as part of an interdisciplinary project at the Pandemic Disaster Preparedness Center. And thank you, Annelot, and you have 15 minutes to give us a brief on your research.
Thank you for the introduction. Hi everyone, my name is Annelot Broerze. I'm from Delft University of Technology, and today I'll be talking about high-resolution modeling of spray strategies for marine cloud brightening. And maybe to start off, usually I start with talking about what is marine cloud brightening, but I think many of us know already because the session is called like that. So I will start with something else, and that's that I'm from the Netherlands. And some of you might have been there, some of you might have not. I live here, that's in The Hague, that's next to Delft. And many of you know probably that Netherlands is really a country where there's a lot of water. And also we have a lot of challenges with water. And we are really known for that. So the first day that I was here, a few people came to me and like, oh, you're from Delft. Probably you will do hydraulic engineering then, because the Dutch people are good with building dikes, right? And I was like, yeah, sort of. I'm doing something with water, but not actually dike building. But if we had no dikes in Netherlands, we wouldn't have the Netherlands, because we're actually below sea level. And so because of this risk that we are really good at building dikes. We call it a shut-off dike. And then we have these delta works. So we have a lot of engineering experience with water. And I think the next water engineering challenge is marine cloud brightening. So that's what I'm going to talk about today. For those who do not know about marine cloud brightening, I will shortly give a summary. So courtesy to SRM 360, which is an amazing platform making animations. And so marine cloud brightening is a strategy where we focus on enhancing the reflectivity of low clouds. And we do this by spraying salt water droplets, and the salt water droplets then evaporate. The salt particles get moved to the cloud base through updrafts, and there act as cloud condensation nuclei. And the water that condenses on these salt particles then form new droplets, and more droplets in a cloud is more reflectivity, which is called the Twomey effect. And in Delft, we are focusing mainly on the modeling of marine cloud brightening, high-resolution modeling. And we have different packages. So we have LES modeling, we use DALES. And we have a parcel model, which is really focusing on 1D dynamics and cloud microphysics. And we try to answer the questions like how many droplets should we spray and what size, and how many sea salt crystals actually reach cloud altitude under different environmental conditions, how many sea salt crystals are activated through droplets, how does the radiative response change, and what are the mesoscale cloud feedback effects. Well, of course, I can't talk about 2 models and all these questions in 15 minutes, so I'll just focus on... Yes. I'll just focus on 2 questions. So on the plume dispersion, how many salt crystals reach cloud base, and how does the radiative response change for large eddy simulations? And for this, we will use the Eurex Fire showcase. It's observation data obtained on the coast of California, which is an area with a lot of stratocumulus clouds, which are clouds that we are aiming for with this method. And I'm going to focus on showing what the effect of different technologies that are being developed is for marine cloud brightening. So we have effervescent spraying, which is one of the technologies that has been used at the Great Barrier Reef experiments. We have rallyjet, electrospray, boa burst atomization, and superheated atomization, which all my colleagues in Cambridge are working on very nicely. And all these technologies have different challenges, but in the end they all want to obtain the same criteria, such that they have salt particles with the right size distribution and with the right production rate, such that we can have this cloud brightening effect. But these come with different challenges, and one of them is that spray generation is not ideal. So many particles that are generated are not actually in their size range, and therefore there's an excess water. And this water, which then gets into the atmosphere, makes the atmosphere cooler. So if you put water and then it evaporates, it leads to a cold plume. And if air is cool, then it goes down instead of up. So that's what we are focusing on. So for the experiments that I'll be showing in LES, I based my data on the prototype data of superheated atomization, which has been provided by Edmund here. And I'll be doing 4-hour seeding simulations with single mode aerosol size, Eurex Fire, and low background cloud droplet number concentration. So we'll focus on 2 simulations, one with a lot of water and one with an optimal amount of water. And with optimal, we mean that all droplets that are generated are within MCB range. And both have the same particle spray rate of 10 to the power 15 and 62 median diameter, which are both considered to be numbers that are within the MCB range. And we put this information in the LES model. So we have a model that is 4D, computing temperature, humidity, and wind fields. And in this pink box, I'm not sure if it's pink for you, but it's supposed to be pink, we add salt and water, and the salt water then disperses through the atmosphere. So here you see the water perturbation, here temperature perturbation, and then the salt move to the cloud and then get activated to cloud droplets. So that's a bit of a idea how it looks in LES. So then the question is how many sea salt crystals are reaching cloud base for the different water use cases. And we see that 80% lower concentrations at cloud base in the excess water use scenario due to this evaporative cooling effect. So what I was just saying, if you add water to the atmosphere, it cools, and then the plume doesn't go up as quick as you wish it would, and therefore an amount of salt doesn't reach the cloud. And this effect is about 18% in these simulations. But if you would add another component, which is that the salt can also be taken up by the ocean, then it's even stronger. So just now we had the solid lines, and if we include the effect of salt deposition, then the effect grows from 80% decrease in salt cloud-based concentrations to 32%. And here I show you a picture of the Great Barrier Reef experiment, and here you see this plume that lingers a bit close to the ocean. So yeah, it's really important that we minimize this amount of water that is used such that we have enough salt at cloud base for the brightening effect. So those are the key takeaways of this part. So spraying excess water leads to evaporative cooling, hampering the vertical dispersion of salt. The plume lingers closer near the surface, and therefore more salt is taken up, and this leads to lower cloud-based concentrations, and therefore spray technology should be optimized in terms of water use. So the next component is how does the radiative response change? So we simulated this, and then I will show you now a video of the shortwave upward radiation. And we see that this salt water spraying with prototype data of the superheated atomization leads to cloud brightening in the form of Gaussian plumes, which are really similar to ship tracks, and which is well, great that we see it. But of course, there are also different components that we still need to discuss. So in the 4th hour of salt water spraying, we have the average salt concentration at cloud base, which is up to about 10,000 particles per cubic centimeter, which activate to cloud droplets. And for this, we use a saturation activation parameterization. And it leads to a maximum albedo of 0.26, but a mean albedo in the plume of 0.17. And another thing I would like to discuss is the so we have this salt activation parameterization, and in many papers it says, okay, in stratocumulus clouds it's sort of normal to have this cloud droplet number concentration of about 500 particles per cubic centimeter. But I also talked to someone who did observations, and he saw peaks with 2,500 per cubic centimeter. And so here you see these delta albedo differences for these different cases, and those are really significant. So I think it's also very important that if we were to go outside for field trials, that we really also get information on this, because otherwise we really under or overestimate the possibilities of marine cloud brightening if we don't have this number right. So, summary of the radiative response, we saw these Gaussian plumes forming, and then we saw delta albedo between 0.17 and 0.34, and mentioning that this optimization of the activation parameterization is very important for really understanding the cloud adjustments. So, to summarize, well, to look into the future actually, so what we are doing in the coming months, years, is more simulations of different spray strategies. So timing, different particle spray rates, a moving sprayer, because we saw quite a narrow plume just now, and different spray technologies, because I just showed only the superheated atomization, but there's a lot of good work going on the different technologies as well. And we want to do this in different environmental conditions, such that we really understand this salt crystal delivery to cloud base. And also we want to do longer simulations with and without the Lagrangian approach on a larger scale. And we want to do this similarly to cloud botany. And maybe you don't know what cloud botany is. It sounds a bit like we're having all these green leaves or something, or trees, but actually it's just another way of saying that we have a lot of different ensembles of a similar simulation, such that we can do uncertainty testing of different parameters. So that's also what we're working on. We have a new GPU accelerated LES version for this, including an extensive microphysics model. And so we can really improve the understanding of all that I've just shown. And then something that's even more important is that we can, of course, stay in the modeling, but in the end, if we really want to believe our models, we need to validate them. So we're planning a single plume experiment in the Netherlands for next spring. And currently we're designing this experimental and technical plan with some work about engagement and communications. And so to touch on that, so we're considering different methods of actually spraying this salt water in the atmosphere. So many of you have probably seen the picture of the ship with a sprayer on it. But we also know people who actually have a wind turbine which has been upcycled that can pump seawater from the ocean and then nebulize it, the seawater which is partly desalinized in the air. And then, of course, there are some pros to that because you can directly use renewable energy. And you're also spraying from cloud altitude. But then on the other hand, there's also a lot of logistical challenges because the material you need for this spraying is really heavy. And so these are all things that we are considering. And also a wind turbine have wake effects, and maybe that makes the stratocumulus cloud disappear. So it looks cool, but not sure if it's the best option. And then this is more the technical plan, but even more important is, of course, the communication and engagement. So for that, I'm going to the biggest festival of the Netherlands this year, Lowlands. And I'll be standing there on the podium asking people about climate intervention, what they think about it, about MCB field trials, should it be part of a climate action plan, and how do people want to be involved. So if you have any input on that, what do you want to ask 60,000 people, then hit me up as well tonight at the dinner or tomorrow. So with that, I'd like to end. And thank you for listening. If you have any comments, ideas, you can ask them later, or you can send me an email or hit me up. Yeah, thank you.
Thank you, Annelot, for saving us 1 minute, 30 seconds. So let's move to the next presenter. The next presenter is Erin, who is a senior PhD researcher at the University of Illinois, Urbana-Champaign in the US. Her presentation is entitled Efficacy of Mid-Latitude Marine Cloud Brightening Strategies in Combating Global Warming and their impact on precipitation. Yeah. So as I said, she's a senior PhD researcher in the Department of Civil and Environmental Engineering. And her current work is, she's currently working on exploring potential climate outcome of marine cloud brightening under a different deployment strategy, and with the aim to determine what triggers a negative climate outcome and how we can create the most uniform and equitable impact. Okay, Erin, you have 15 minutes.
Great, thank you for the introduction. I think that covered it all, so I think I can get started. I think we all know what marine cloud brightening is, especially with that great introduction we just had with the last presentation. So previous marine cloud brightening, or MCB, studies show that while it could reduce surface temperatures, it also commonly results in uneven cooling patterns and a perpetual La Nina-like sea surface temperature response. And I've shown some examples of this on the slide here. The top is from the study Rasch et al. 2009, where they simulated cloud seeding over 70% of the ocean surface. And the bottom two plots are from Hirasawa et al. 2023, where they targeted cloud seeding over subtropical regions. The surface temperature change patterns here strongly resemble composite La Nina sea surface temperature anomalies, suggesting that conditions are in a perpetual La Nina state. And you can also note the uneven cooling patterns in each of the plots here. Chen et al. 2024 explores susceptibility-based cloud seeding strategies with the model CESM2, which is based on the amount of incoming solar radiation and clouds present within a region. They find that simulating MCB over 5% of the ocean surface most susceptible to cloud seeding results in these uneven cooling patterns and the La Nina-like state. And this is the circled plot here, which resembles those left plots as well. They find that by targeting least susceptible regions over a larger oceanic region leads to a more uniform cooling pattern and also avoids triggering La Nina. They find that cloud seeding 20% of the ocean surface least susceptible to cloud seeding results in the most uniform impact of the experiments they tested in that study. So shown here are the cloud seeding masks from Chen et al. 2024, which signifies where MCB is deployed in the model. And the study uses monthly varying masks, meaning that the regions that MCB is deployed in changes from month to month. So the top mask represents cloud seeding for December and the bottom for June. Note that the 20% scheme largely covers mid-latitude regions, and the 5% scheme largely covers tropical and subtropical regions. We adapt the 20% scheme into new cloud seeding masks, which also cover 20% of the ocean surface, but over more uniform mid-latitude regions within a single hemisphere at a time. And these more structured cloud seeding masks are more ideal for model intercomparison, as they don't follow that precise grid box to grid box structure that you saw in the previous masks from Chen et al. So we simulate MCB also with the Community Earth System Model version 2, fully coupled with 3D ocean and active land and sea ice. I won't get too into the weeds about the model here, but MCB is simulated by artificially increasing the cloud drop number concentration of clouds within the boundary layer to 375 per centimeter cubed. And this is within the model grid boxes specified by the cloud seeding masks, so the purple regions that you see in each of those maps. And we simulate MCB in this way because it bypasses uncertainties within the CESM2 model regarding the aerosol activation scheme. So here we're just assuming MCB has been deployed and successfully brightened those clouds. Our MCB experiments are initiated in 2035, which is when each experiment branches off of the control or the first member of the 16-member ensemble of simulations performed from 2015 to 2100 following the moderate future warming scenario SSP2 4.5. And the target of our simulations is to restore present day or control 2020 to 2039 temperature and precipitation conditions. We first started our study by exploring sensitivity experiments which test single hemisphere deployment of MCB in the local summer months, which are the months with maximum incoming solar radiation and therefore are more likely to induce cooling, and within the local winter months, which are less likely to induce cooling. And these experiments are performed for 20 years from 2035 to 2055. And we first start by looking at the surface temperature response of our sensitivity experiments compared to the present day, or again, controlled 2020 to 2039 level. And we find that summer seeding in either hemisphere, which is those top two plots, achieves significant cooling up to 3 degrees Celsius, but these cooling patterns are non-uniform, largely cooling oceanic regions and largely contained to the hemisphere that MCB is deployed in. For our winter seeding strategies, there is minimal cooling that is achieved, but the impact on temperature is a bit more uniform. We do note, though, that the change in temperature here is similar to the change from climate change, SSP2 4.5, with the exception of a couple of regions within the ocean that are cooled by these strategies. We also consider the impact of our MCB experiments on precipitation rate, focusing specifically on whether or not our MCB experiments shift the intertropical convergence zone, or the ITCZ. And this is important because shifting the ITCZ could change precipitation patterns in populated equatorial regions, which could in turn affect their agriculture, net primary productivity, etc. So here I show some plots that approximate whether or not the ITCZ shifts from our MCB experiments. So the black line represents the MCB experiments and the gray the control. Our summer seeding strategies result in a shift of the ITCZ toward the opposite hemisphere that MCB is deployed, and this is highlighted by those blue and green boxes on the slide there. Whereas for our winter seeding strategies, the oscillations are a bit more similar to the control, suggesting that the ITCZ may not shift. The impact on precipitation from our winter seeding strategies is much less significant. And we also confirm this approximation by analyzing the spatial distribution of precipitation rate response. So our summer seeding strategies result in changes of precipitation along the equator, which is around where the ITCZ is located. And we see that there are increases and decreases in either of those plots that signify that MCB is shifting the ITCZ toward that opposite hemisphere. Whereas for our winter seeding strategies, there is minimal precipitation rate response that is statistically significant. And I'm not sure how well you can, it's all right. That suggests that the ITCZ may not shift here. So just to summarize quickly our sensitivity experiments, our local summer seeding strategies result in uneven cooling patterns and shifting of the ITCZ, suggesting that these are not viable climate intervention strategies. And while our local winter strategies do avoid these side effects, they do not produce enough cooling to effectively help mitigate the impacts of climate change. Therefore, we create two new scenarios where we extend cloud seeding into 6 months of the year in the local fall and winter, in either hemisphere. So these experiments are performed for 35 years from 2035 to 2069. So these are still single hemisphere MCB experiments. And we find that fall plus winter seeding in either hemisphere results in a larger impact on surface temperatures than cloud seeding in the local winter only, but these cooling patterns are non-uniform, largely cooling oceanic regions. And while our fall plus winter seeding in the southern hemisphere strategy does distribute this cooling a bit more globally, these cooling patterns are of course still not ideal. And we also note that there is a shift in the ITCZ for both of these strategies, again suggesting they are not viable. So to avoid these side effects, we combine the fall plus winter schemes into a single scheme where MCB is deployed in each month of the year and for 6 months of the local fall and winter in either hemisphere. And we first look at the global annual average surface temperature and precipitation rate for our fall plus winter in both hemisphere scheme, the 20% least susceptible scheme from Chen et al. 2024, which I mentioned at the beginning of the presentation as the scheme we based our cloud seeding masks on. And I also conclude the control and present day level here just as a means of comparison. So we find that fall plus winter seeding in both hemispheres demonstrates a similar performance to the 20% least susceptible scheme from Chen et al. 2024, both maintaining global annual average surface temperature and precipitation rate relatively well throughout this 35-year simulation. However, our combined scheme does lead to slightly more intense cooling than the 20% least susceptible scheme, for instance, in the year 2045. And we also note that the fall plus winter seeding in both hemispheres scheme delivers a more uniform cooling pattern and avoids shifting the ITCZ, making this the most effective restoration of present-day surface temperature and precipitation rate of the experiments that we tested here. And we also analyze the impact of our MCB experiments on the El Niño Southern Oscillation by considering the Niño 3.4 index. And the Niño 3.4 index indicates whether or not conditions are in El Niño or La Niña based on the sea surface temperatures within the Eastern Pacific. So here we show that the control experiment leads to El Niño and La Niña oscillations every 2 to 7 years about, which is what we would expect from normal ENSO cycling. However, for the 5% most susceptible scheme from Chen et al. 2024, it clearly shows that we are in perpetual La Niña conditions. But we expected this as the surface temperature response suggested that conditions were in a La Niña state. So we'll first start with the sensitivity experiments. For the time period of our sensitivity experiments, 2035 to 2055, the control is in La Niña for 62% of the time. So each of our sensitivity experiments leads to an increase in frequency in time spent in La Niña. So I show each of the percentages of time spent in La Niña in the respective plots here. Our summer seeding strategy in the southern hemisphere triggers the most frequent La Niña conditions of the experiments shown here, whereas for winter seeding in that same hemisphere, we get less of an impact. For winter seeding and summer seeding in the northern hemisphere, we get a very similar impact. Suggesting that the seasonality of deployment for MCB in the northern hemisphere is less important for the ENSO impacts. And we'll also look at the fall plus winter seeding strategies. So for the time period of 2035 to 2069, the control is in La Niña for 55% of the time. So fall plus winter seeding in the southern hemisphere leads to a near 30% increase in time spent in La Niña, whereas for fall plus winter seeding in the northern hemisphere, we get a smaller impact. And we also find that fall plus winter seeding in both hemispheres triggers more frequent La Niña than the 20% least susceptible scheme from Chen et al. 2024. And this is likely due to the fact that we are inducing slightly more intense cooling with our scheme. In conclusion, we created more organized cloud seeding masks with equal cloud seeding area to the 20% least susceptible scheme from Chen et al. 2024, demonstrating similar climate outcomes here. We also show the importance of seasonality for MCB deployment with respect to climate outcomes. For instance, depending on the seasonality of deployment, single hemisphere MCB may lead to uneven cooling and shifting of the ITCZ. For ENSO, we find that southern hemisphere MCB deployment in specifically the summer and fall plus winter months triggers more frequent La Niña than northern hemisphere deployment. And this is consistent with recent work from Rash et al. 2024, where they showed that cloud seeding within the Southeast Pacific triggers La Nina. However, here we show the seasonality aspect to this, as cloud seeding within the summer and fall plus winter months in the Southern Hemisphere triggers more frequent La Nina than cloud seeding in the local winter only in the Southern Hemisphere, suggesting it is not only the location, but the seasonality of MCB deployment, which is important, within the Southern Hemisphere, of course, which is important for those ENSO impacts. And of the experiments we tested, fall plus winter seeding in both hemispheres delivers the most effective restoration of present-day surface temperature and precipitation rate. Our future work is focused on looking at the impacts of our MCB experiments on polar sea ice, so if anyone's interested, I'm happy to chat more about that afterwards. And if you're more interested in the results, please scan the QR code. We have a preprint out right now, and thank you.
Thank you very much, Erin. 1 minute saved. That's very important to mention. Yeah, well done. The next presenter is Edmund. Edmund is a PhD researcher from Cambridge University, UK. And his research is on experimental development towards the construction of a sprayer for marine cloud brightening field trials. And he's part of a team that is researching different spray techniques for MCB. And he researched the potential of several candidate sprayers to meet the requirement of MCB arriving to superheated atomization. I got no idea what that means, but I'm sure he will make okay. He will tell us. So Edmund, you have got 15 minutes to give us the substance of your presentation. And please remember to put down your questions, because at the end we'll have an open session for a Q&A, open Q&A session. Thank you very much.
Okay, thank you for the introduction. Hello everyone, it's great to be here from Cambridge, the Centre for Climate Repair, here with 4 of my colleagues. I can see 2 of them have turned up. That's good, right. So I came across marine cloud brightening about 5 years ago, and I was very interested in the subject because I thought it's something which we're going to need. I'm not advocating its wider use, but it seemed highly likely to me that it's the kind of technology that we're going to need in my lifetime, at least for some regional cooling, which is already being tested over the Great Barrier Reef, as you know. Then when I discovered there was only 3 groups in the world working on this technology, the actual way of producing the sprayers to produce the correct size droplets, I decided that that's what I would go into. So I researched all of these different ways. I'm an engineer, so this is going to be a fairly technical or dull presentation, depending on how you take it. But this is about the experiment that I've built. So superheated atomization. This was suggested to me by one of those groups, Armin Newcomen's first, he was heads up the first group that started to develop sprayers, and it was a concept that Dan Harrison, who hopefully is here somewhere, there he is, it was his idea to try applying this for cloud brightening. So superheated atomization, I will tell you now what it is you have your, right, is that laser pointer working? Okay. You have your seawater traveling down this tube at above 100 degrees, but it's under pressure, so it can't boil. And then it reaches that constricting part of the nozzle there, and it starts to accelerate, and so it effectively starts to boil, and these little bubbles start to nucleate in there. And then when it's exposed to atmospheric pressure out here, those bubbles rapidly grow, and they blast apart the liquid around them in this kind of ballistic atomization, and that liquid forms into little droplets that we hope are the correct size for marine cloud brightening. So about 4 years ago, I was doing a master's at Cambridge, and I suggested to a rather shocked supervisor that I was going to build one of these experiments. They carry a certain amount of danger with them. So this is what I put together on a £2,000 budget. That is the sprayer. I then took that started a PhD under Hugh over there, and took that into this laboratory where it's nice and empty. I was on my own, so I've got that sprayer here. And then this box over here is measuring the size of the particles that I'm producing, which was borrowed from a company down the road. I should point out, there's so Dan and Armin Newcomans had seen that you can get these submicron droplets from superheated atomization, but before doing this, I trawled all of the literature I could find on superheated atomization of any fluid, and no other experiments apart from one, possibly two, showed that you can get these small droplets. But anyway, I turned this sprayer on and turned that box on, and there they were, plain to see, is producing submicron droplets. So that was an encouraging start to the project. To point out, this is a slightly different sort of sprayer to what the other guys were testing, but still getting the similar sized droplets. Okay, so then this is how it's looking now in our laboratory. I've filled up with some stuff and some people. There's now got Jake there, who is unable to attend, unfortunately, and Yashas working in the lab with me. So what you're looking at here, okay, we've got my sprayer is under here in this area, in that area, and we've got the spray the nozzles are inside that tube up there. They're spraying out the seawater here, and it's getting drawn down this tube and then sucked out into these particle detectors. We've now got 4 of these boxes, but they all measure the size of the salt crystals that you're producing. And all three of us are developing different sorts of sprayers. There's four different sprayers in total being produced in this lab, but they all have to go through this same process of measuring the size of the salt crystals they're producing. So just to put some numbers on what Annelot was alluding to, the actual requirements for marine cloud brightening, that you spray droplets at this size, 120 to 2,000 nanometers, and they will evaporate to a dry salt crystal, which is 30 to 500 nanometers. And that's the kind of size range that you want. You want a narrow size distribution. That just means that you don't want too many outside of that range, because they can have detrimental effects, some of which Annelot alluded to. There's other effects on the clouds. There's, to a greater or lesser degree, contested in the literature, basically. You want a controllable distribution. That means that you want to be able to change the size within that range. I'll come to that later. And you need to produce a lot of them, 10 to the 15 per second per spray source, which is decided as the minimum amount that you're going to need to see an effect on the clouds. So that's the amount you need for a field trial if you're going to be able to see what's going on. And you want a feasible amount of energy to do this. Okay, so on to some results. So I built that sprayer, developed that fairly gold standard detection system, got some interesting results and wrote those into a paper, which I'm just about to submit. And yeah, I mean, that all sounds fairly straightforward, but it's taken a couple of years. But you can now see some of those results. So right here we've got on the x-axis the diameter of those dry salt crystals, on the y-axis the number of them, and then the curves are called size distributions, and they're showing different distributions for different temperatures. So these lower down ones are 150 degrees, top ones are at 250 degrees. And so what this is telling you, the important effect of temperature, is that you're getting this narrowing of the distribution and a larger distribution, a taller distribution, but it's not as wide. And the other important fact here is the green shaded area is the range that we're aiming for. And so there's 84% of the particles are in the correct range, and 100% of the particles are all submicron, despite the fact that that isn't really shown anywhere in the literature. So if you want to talk about getting a narrow size distribution, you measure it with the geometric standard deviation, which is what this plot is about. So the lower the geometric deviation, standard deviation, the narrower the plot. So you can see it falling there with temperature. And actually that curve carries on down to 1.85 is the lowest that I've got, using some different nozzles, and that's lower than a typical ballistic atomization like this. Tends to have a wider distribution than that. So that's addressed a couple of those criteria that I was talking about earlier. And the other point is that the mode of this distribution is staying right there on 70 nanometers, the peak of that distribution. So that's not necessarily a good result. What that's telling you is that temperature cannot be used as a variable to move that distribution around, because everything's about using variables and trying to see what the effect is on the distribution. Okay, next set of results. These are talking about production rate. So that's temperature on the x-axis again, and then y-axis is the number of particles that I'm producing every second from my single nozzle, and that's clearly increasing with temperature. And the slightly more interesting or unusual counterintuitive point from the colour scale here, you've got the flow rate. So if you take a couple of points on here, each one of those points represents a size distribution, by the way. So if you take a couple of points there which are at approximately the same temperature, but showing that you are decreasing the flow rate, so this is at a lower flow rate, this one up here, but you're actually increasing the production rate. So if you actually think about that, you're putting less water through the nozzle, but you're producing more submicron particles when you do it. That's an important result there. The other metric that we were interested in is the energy use, the amount of power. So the metric that I was using is the power required to produce 10 to the 15 particles. That would be with approximately using 1,000 of my nozzles is how many you'd need to do that. And the amount of power that would require is shown on the y-axis here against temperature, and it falls down as you increase in temperature. That's falling down to a kind of minima between 200 and 240 degrees, and there's a few different nozzles in this data again as well. But so you're getting that it's getting more energy efficient the hotter you're doing it, and again lowering the flow rate is also making it more energy efficient from the color scale there. And yeah, the minimum is around 300 kilowatts for 10 to the 15. That's about 30% less than Armin Newcomen's and their paper were saying, but it's comparable, which is fairly surprising considering they are using a completely different sort of atomization. It's more energy than what Dan's group have been doing with a superheated sprayer, but theirs is a much wider distribution for other reasons that we were talking about last night and couldn't decide. So just to put that into context, it's something like, I've forgotten how many gigawatts. If you want to make enough particles to reduce global temperatures to pre-industrial levels, and you use Robert Wood's numbers and calculations, that works out at something like 10 Tokyo cities worth of electricity consumption to do that on a continuous rate, or 64 Londons or 60 New Yorks, or whichever metric you want to use. Okay, well the one bit that I haven't addressed is being able to move the distribution around, controlling the distribution. And I haven't been able to do that, but I've got some enticing results on towards that. So these are size distributions, again, looking at standard flashing, standard atomization I was talking about, but then as you move across these distributions, what I'm doing is dropping the pressure down to a point where the boiling is starting to happen inside the nozzle effectively, and what happens is you get this drastic change in the size distribution. So it's moved from here in the MCB range down to much smaller particles, and what that looks like on the sprayer, to put in context, this is a typical of boiling that's happening outside the nozzle. You've got this kind of wide spray angle, and then as it moves inside at lower pressures, you get this narrow spray angle. And this is enticing because if you can get some control over this, then it gives us the ability to move the size distribution around. But it's also inherently unstable and difficult to do. So that's part of the modifications I've been making to the sprayer over the last 6 months. Okay, so if I just go back to those. These are those conditions we were talking about. So we've got them in the right size range, or at least 84% of them. We've addressed the idea of trying to narrow that distribution by using temperature. We're getting somewhere with that. We've got a little sort of hint towards how to control it. Know how many nozzles you'd need to get this 10 to the 15. For mine, it'd be of the order of 1,000. And so that's kind of where I am at the moment. In the progress of the project is going to be in the short term looking at building up scaled up sprayers for field trials. So they'll look something like these are Dan's ones. They'll appear something like this, I imagine. And there's a few tests I've got to run on my sprayer before they go to this stage. And in the longer term, I want to just carry on getting this, all of this, addressing these 2 points here. And the only way to do that is by generating this submicron size distributions and correlating them to different variables. And don't worry about these plots. It's just to indicate this is the kind of stuff. So it's just getting lots and lots of this data, which really doesn't exist anywhere else. And it's the only way to get a more fundamental understanding of what's happening in superheated atomization is to generate these distributions. Yeah, that's all of there's a couple of other applications, which is Annelot alluded to the fact that there's large amounts of water of the wrong side of two larger particles. So that's another project is going to be trying to look at how to remove those using different nozzle geometries or downstream conditioning of the spray, which is another story. And yeah, this is all stuff that I'm going to try and squeeze into a depleting amount of time that I've got left in my PhD. So yeah, okay, thank you. Oh yeah, and I'm doing a poster tomorrow if you want to come and look at it.
Thank you, Edmund, for saving us some seconds, and that's really important. So 30 seconds, exactly. So the last presenter is, I'm not sure, sorry if I pronounced the name wrong, is Tianle Yuan. Is he in the room? Online. Okay. Is it recorded? So he submitted a pre-recorded presentation, and wait, can we pause it a minute? Okay, so he's an associate research scientist at the University of Maryland, and his presentation will be on quantifying the effect of marine cloud brightening across different spatial-temporal scales with observations and modeling studies. So the floor is yours, Tianle.
Hi, thanks for the opportunity to speak. My name is Tianle Yuan. Today I'm going to talk about quantifying the efficacy of marine cloud brightening across different spatial temporal scales with observations and modeling. Before I get into the content, I want to acknowledge my co-authors listed here and funding support from different agencies, NASA, NOAA, and DOE. So for the marine cloud brightening, a key question is, will it work in terms of generating radiative cloud cooling, right, at a global scale? And that question could be answered in different ways: modeling and observation. So far, we haven't carried out large-scale experiments, so observationally we have to rely on analogues. And ship emission is probably one of the best analogues we have, because ship emitted SO2, for example, accounts for about 10 to 15% of total anthropogenic SO2 emissions prior to 2020. And when we looked at the literature, there are two camps. Using global climate models, we consistently see results of on the order of negative 0.1 watts per meter square with a range. Some of the studies are listed here. While on the observational side, the estimate is much smaller. For example, Peters et al. Tried to find signature of ship emissions impact on clouds or radiation, and they reported that they couldn't find any, even for one of those busiest shipping lanes. Schreier et al. In 2007, they used detected ship tracks to estimate the radiative forcing and come up with a number that is 1,000 times smaller than the GCM. So in this study, we decided to investigate what does ship emission matter, or in other words, do marine cloud brightening schemes work? At a local scale, we know for sure that marine cloud MCB works, as illustrated by many examples of ship tracks. So these are ship tracks over North Pacific, and clearly the ship track clouds are brighter than the background clouds. So at this scale, marine cloud brightening works. But these ship tracks are relatively rare, and they are accidental, not intentional. And we know for sure that they are produced by ship-emitted aerosols interacting with low clouds. And we also know that they are excellent natural experiments for understanding the physics of aerosol cloud interactions and therefore MCB. Now, if we zoom out a bit at local scale, where many previous studies report hard to detect impacts from the ship emissions, right? But in the Southeast Pacific, there have been several studies reporting that the conditions are just right that we can detect the signatures of ship emissions. For example, panel A shows the climatology of cloud droplet number concentration observed by MODIS, a satellite instrument. Panel B shows if we do geospatial kriging on the data and create counterfactuals for a scenario that there is no ship emissions, what the ND would look like. And if we differentiate these two, we get panel D, which shows the impact of ship emissions on ND distribution. Alternatively, we can build up ship emissions impacts on ND from bottom up. That is, we pick the Southeast Atlantic, we use machine learning based models to detect ship tracks, and then we can quantify the frequency of ship tracks, coupling that with kind of mean ND perturbations inside a ship track. Then we get panel C. Now, to be more precise and accurate on the forcing from ship emissions, we want multiple ways to do estimate, right? So we decided to look at this problem both from bottom up and top down. Top down is using the kriging method to estimate counterfactual scenarios based on geospatial kriging, and this gives us top-down estimates of the forcing or cloud changes associated with ship emissions. We can also do bottom-up, and for bottom-up approaches, we can choose either use ship track frequency as an indicator, or we can use the ND perturbations estimated from kriging or chemical transport models. We call them bottom-up adjust. And both approaches relies on cloud adjustment functions. That is the cloud fraction adjustment to ND or liquid path adjustments. And if we look at the seen albedo sensitivity to ND, which is kind of the sensitivity introduced by aerosols, and that's a key parameter for MCB or aerosol cloud interactions. Most of the uncertainty comes from the two adjustment functions, cloud fraction and LWP. And our approach is to use ship tracks as natural experiments to derive these functions. Without going into any details, just as illustrations, we show LWP adjustment function sensitivity to ND, so that's cloud adjustments, as a function of background conditions or background cloud properties. So it's not a constant, as you can see. It has dependencies on different variables, and we want to take these kind of background sensitive dependent functions and use them to bottom up estimate the cloud forcing introduced by ship emissions. And this is the cloud fraction. Without going into details, cloud fraction is a exponential function of, say, cloud background ND or effective radius. So it's very sensitive to background conditions. Now, when we apply these functions to the data, this slide summarizes the results. The top row shows the estimate from Schreier et al. In the Southeast Atlantic. So the forcing is on the order of negative 0.01 watts per meter squared. And if we use bottom-up approach similar to Schreier et al. By looking at ship tracks, then the forcing goes up to close to 0.1 watts per meter squared, so five-fold a jump. This indicates that Schreier et al. Probably missed a lot of ship tracks. But both top-down and bottom-up adjustment-based estimates put the forcing in the shipping lane to be about 2 watts per meter squared, an order of magnitude higher than even the bottom-up ship track density. So this sends us two main signals. One, marine cloud brightening or aerosol cloud interactions is in terms of forcing, is pretty strong in the Southeast Atlantic within the shipping lane, right? Second, ship tracks are great indicators of what's happening, but in terms of forcing, they contribute very little, about 5% based on our estimate. So they are really just a tip of the iceberg. We know that marine cloud brightening or aerosol cloud interaction is happening, but they don't tell us the full picture. Now, if we further zoom out, taking the approach of bottom-up adjustment approach to look at the global impact. And fortunately, we had a opportunistic or inadvertent experiment happening in 2020 when international maritime organizations regulated the ship emissions of SO2 in that year, and which effectively decreases the ship emissions of SO2 by more than 80%. The upper panel shows the climatology of detected ship tracks, the tip of the iceberg, and we see major shipping lanes. In 2020, however, across the globe, the detected ship tracks decreased by a large magnitude. So that's indicating the impact of the fuel regulation, right? But to estimate the full impact, remember, we have to look at the whole picture, not just the ship tracks, because they, in terms of forcing, they contribute relatively little. So we use a chemical transport model to model the impact of ship emission regulation on the aerosol optical depth and ND. So that's what we show here. Top panel shows the impact on the AOD and compared to the total impact from pre-industrial and present day. So over the oceans, along major shipping routes, we can see the impact is actually relative to pre-industrial and present day. It's a significant amount, especially in regions like North Atlantic and North Pacific. In the bottom row, it's showing the same thing, but for ND. Same picture. In the North Atlantic and North Pacific, the ND impact is significant at some regional scales. Now, if we scale this, do the calculation using bottom-up adjustment approach, we can estimate the total forcing and break it down into 3 panels that's shown in the left column. So the top panel shows the Toomey effect, the forcing from Toomey effect, forcing from LWP effects in the middle, and cloud fraction adjustment effect in the bottom. And we can see that the major contributions are coming from the Toomey effect and the cloud fraction adjustment. The total forcing from the IMO 2020 is estimated to be 0.2 watts per meter square with an uncertainty of 0.1. And this number is in broad agreement with several modeling studies that looked at the same issue. So which gives us kind of confidence that the order of magnitude estimate is probably right. So on the order of 0.1 or 0.2 watts per meter squared average over the globe. And also in the regional sense, we looked at Southeast Atlantic, completely independent top-down approach, and our estimates agree with each other quite well. So this tells us that the total emission from shipping industry and its forcing are not insignificant, and the total forcing from ship emissions is probably on the order of 0.1 watts per meter squared. The exact range is still uncertain, because even for our approach, there are a few sources of uncertainties as discussed in our paper. But this would suggest that MCB has already happened in terms of inadvertently by global ship emission, right? Now, using this forcing estimate, we can also calculate temperature response. Here we did a simple analysis using energy balance models. It's a 2-layer energy balance model. And we input the forcing in 2020 as a kind of a shock type of forcing, because it's not, the regulation is not like new regulations apply to every year. So the forcing is kind of a shock type of forcing, 0.2 watts per meter squared, put in the model and see the temperature response. And the range of uncertainty in terms of forcing is also plotted in the shades. So the punchline is that based on this estimate, the global warming rate for this decade, 2020s, will double the long-term mean warming rate since 1980s. And the enormously warm 2023 warmth is within the range of possibilities based on our model estimate. And this gives this summary of my talk, and thank you for your attention.
So if you have any question? 1, 2, 3, 4, and 5. Okay.
Thank you so much. Greetings, everybody. So I have only 2 questions. One is for Karen. Firstly, I would like to be part of this scientific rocket science class. I've never thought in my life that I'd be part of something like this. Yeah, it's too technical for me to understand, but I'm learning. There are a lot of graphs there. I don't see anything. I don't understand anything on the graphs that are being presented. But yeah, on that note, Karen, you've mentioned on closing your presentation, you've mentioned something on taking your presentations to the music festival as a way of exposing the kind of work that you are doing. So I was wondering if, do you perhaps suggesting to have a simplified version of this kind of work, because I'm anticipating where you're going to do these presentations. It's a music festival. It's not a formal conference, so it will be musicians and and artists, you know. So I'm just wondering and curious on that. And then this one goes to all of the presenters. On the studies you've done, the focus seemed to be on cooling the atmosphere and the earth. But now I'm missing something here on the marine life, on the impact of the marine life, the species that live in the marine. What impact this technology will bring about? Are there any research so far being done on that? And then secondly, what fuels do these ships are being powered by? Thank you.
Thank you very much. Let's shall we just collect all the questions and then you will react to them?
I'm struggling to hold those three in my head. I can't have any more. They weren't even for me. Just the middle one about marine life. It's not. So you're sucking. I'm not sure what you mean, because you're drawing water out of the sea and spraying it into the air. So that process. I mean, you might suck up the odd fish potentially, but it's not. It's not a. But it's not. That part of the process isn't going to be. Isn't massively dangerous. Depends on what context you're looking at. If you're talking about doing it on a global scale, then there's all sorts of effects that lots of people in this building are trying to model, and they could potentially have effects. If you're talking about doing it on a local scale, like what's happening at the Great Barrier Reef, you're trying to reduce the temperature by a small amount. I'm sure there will be some effects on the marine life. You have to pitch that against the whole barrier reef being dead in 20 years. So these things have to be put in context. But I haven't heard of any specific effects directly on marine life from the actual process of doing the spraying. Okay.
So for marine cloud brightening, the idea would be to spray these sea salt aerosols into the air, and there would be atmospheric chemistry effects of that. Specifically, if you're thinking about like marine life effects, there would be processes of the sea salt aerosols within the atmosphere that could affect mercury concentrations, which could in turn affect bioaccumulate in marine life, and consequently we eat seafood, so that could affect humans as well. Sorry.
I think to add to that part, it's also something, if I talk about marine cloud brightening to just people who are not familiar with the topic, they always ask like, okay, and that salt that you spray in the air, does it come into my garden then and ruins my plants? So it actually, also in the context of public acceptance that we are going to study at Lowlands, is really something that also worries the general public. Even though it's sort of just sea salt, it's still adding something to the atmosphere. So, and then maybe, so you asked how I'm gonna do this public acceptance study at Lowlands. I'm indeed not going to stand on the stage in front of 60,000 people. That would have been cool, maybe I'll try, but but we're actually having this interactive installation. So first we have this sort of climate warm-up where people, we divide them between humans and planets, and they intervene with each other. So for example, with like some handmade ventilators or water sprayers, such that they understand the interaction between the Earth and humans. And after that, we have this interactive discussion table to really go through the whole range of climate adaptation, mitigation, and then the role of climate intervention in this, and then discuss what their thoughts and worries are about this method, and also how they want to be involved in future field campaigns. So yeah, it's a bit broader than what I just said, yeah.
You're not going to sing a song?
Well, if you come, I will sing a song.
Thanks to our presenters for the wonderful presentation. My question goes to Erin. When you were discussing your results, you did mention that when you did the fall and the summer spraying, you realized that the shifts in the ITCs you had reduced. Yes, but the question is, even a 2-degree shift in the ITCZ implies a lot, because that's about 220 kilometers of shift. And how do we address this when we're trying to implement this? Because my country is Ghana, it's quite small. If you shift the ITCZ 220 kilometers away from us, and 60% of our population depends on rain-fed agriculture, I think that is huge. So how do you quantify these? Yeah.
So I just wanted to make sure I understood. You were talking about the fall plus winter strategies, but the single hemisphere strategies or the combined scheme? Yeah, I mean, this is reduced, but I think we could maybe address this in future work. This is kind of like the best that we did in the study and of the experiments that we tested, but certainly it's not perfect.
Yeah, but my point was in your final conclusions, you made it seem like that was an ideal thing to have, and I'm just pointing your mind to that. It's not even ideal with even 2-degree change.
Right, I definitely understand that. I guess my point was of the experiments we tested, it was the most effective, and I hope I put that in my slides of the experiments I tested, but certainly you have a great point there.
Thank you. Number 3.
Number 3, hopefully slightly easier questions. For Edmund, but yeah, two questions for 2 presenters. For Edmund, you're spraying hot, salty water through a metal apparatus. Doesn't it like corrode the hell out of it?
Stainless steel supplies, okay.
Nice.
Stainless steel lasts pretty well. You could use Hastelloy, which will last longer, but yeah, it's not a big deal, no.
And for Erin, following up on the first question, sorry, where does mercury come into it?
So sea salt aerosols affect the halogen concentrations within the atmosphere. So it would change. I guess there are 2 different types of mercury we see in the atmosphere. You have the elemental mercury, which has a longer lifetime, and then you have its divalent compound, which is more rapidly deposited. So the perturbation in halogen concentrations could, in turn, kind of shift more of the elemental mercury to that more rapidly deposited form, which would see more deposition of mercury, more likely over oceanic regions, because that's where you're deploying the marine cloud brightening. So I'm planning on doing that for my final PhD project. So
Thank you. Number 4.
I have a question for Ed. So how many nozzles do you have in, like, if you imagine your future sprayer, how many nozzles would you have within that sprayer? And could you imagine some energy saving from having many nozzles within the same sprayer?
Yeah, if you're talking about that scaled up one where I showed the pictures, like Dan Harrison's ones, I think they've got about 600-ish on there, and mine looks like it's of that order, getting towards 1,000. That's using the nozzle that I've tested so far, and to be honest, the test ones which will put out greater flow rate and then potentially be less nozzles. Yeah, that doesn't really affect the energy saving. There's an efficiency saving in terms of the amount of infrastructure if you don't have to make so many nozzles, but yeah, no, that doesn't really affect the energy.
Thank you. One last question.
My question was just, have you calculated the water flow for the 1,000 nozzles? And how does that compare to the water flows that we saw modeled with the LES? So for both of you, I guess.
I didn't know I was going to run a marathon.
What, milliliters?
Yeah, milliliters per second.
A second.
Yeah.
Yeah, I think mine is, yeah, how was it? It's about half a milliliter a second for one nozzle, so that times 600, 300 milliliters a second for 10 to the 15, and that's about what you had. Yeah. What was the question? Have I calculated that? Yeah, so that yes, so that. Yes, so the idealised flow is the amount that's turning into the submicron particles that we're choosing. But do you remember I was saying there's only actually about 9% of mine is going into that, and so the other 90% is the unidealised one. But I did notice that those numbers weren't a factor of 10 out. They were a factor of 30 or 20. Yeah, I think I knew you can notice that. Anyway, I think my results have improved since I gave those to Annelot. So I think it used to be 4%, now it's 9%, something like that.
Yeah, I think you already mentioned it, but indeed the data you provided me was for 10 to the power 15 particles per second, and indeed either all droplets that are formed or just the droplets within the MCB range. Yeah, so that was the difference in the numbers. Yeah.
I guess we don't know the droplets that are too large. We don't know how many of those are sort of large enough to be just falling straight out, right? And might not be included in the evaporative plume calculation, or shouldn't be.
Yeah.
Okay, thank you very much for making it up to the end. I really appreciate your participation to this session, and it was a pleasure for me to moderate this session. We have 4 bright minds researching marine cloud brightening, and they quite educate us a lot on the topic. Thank you very much, and thank you for making sure that you stay in the 15 minutes that we're giving to you. And because of that, we went a little bit ahead of time, but nothing to worry about. Thank you very much. And bye-bye.